Welcome to this coding walkthrough. In today's session, we will explore LeetCode problem number 1033, titled Moving Stones Until Consecutive. This problem challenges us to determine the minimum and maximum number of moves required to align three stones on a number line in consecutive positions. We'll break down the problem, analyze its constraints, and discuss efficient approaches to solve it. Let's dive in. In this problem, we are given three integers a, b, and c, which represent the positions of three stones on a number line. These positions are distinct, meaning no two stones share the same spot, and they lie within the range of 1 to 10 to the power of 9. The goal is to move these stones in such a way that they end up in consecutive positions, where there are no gaps between them. To achieve this, we can move one stone at a time to any unoccupied position on the number line. The challenge here is to calculate two values: the minimum number of moves needed to make the stones consecutive, and the maximum number of moves it could take to do the same. The input consists of three integers representing the positions of the stones, and the output will be a list of two integers. The first integer in the output represents the minimum moves, and the second represents the maximum moves. Let's explore an example to understand this better. Imagine the input positions are a equals 1, b equals 2, and c equals 5. The output for this case would be 1, 2. Here's why. To minimize the number of moves, we can take the stone at position 5 and move it directly to position 3. This results in the positions 1, 2, 3, which are consecutive, and it takes only one move. On the other hand, to maximize the number of moves, we can take a step-by-step approach. First, move the stone at position 5 to position 4, and then move the stone at position 4 to position 3. This process takes 2 moves in total. Thus, the minimum number of moves is 1, and the maximum number of moves is 2. Now consider another example where the input positions are a equals 4, b equals 3, and c equals 2. For this case, the stones are already in consecutive positions, 2, 3, 4. Since no moves are needed to make the stones consecutive, the output is 0, 0. This highlights an important edge case: when the stones are already consecutive, both the minimum and maximum number of moves required will be 0. The problem handles such scenarios by checking the initial positions before attempting to calculate the moves. Finally, let's look at the case where the input positions are a equals 3, b equals 5, and c equals 1. The output here is 1, 4. To minimize the number of moves, we can take the stone at position 5 and move it to either 2 or 4, resulting in consecutive positions 1, 2, 3, or 3, 4, 5, with just one move. For the maximum number of moves, we can move the stones one step at a time. First, move the stone at 5 to 4. Then, move the stone at 4 to 3. Next, move the stone at 3 to 2, and finally, move the stone at 2 to 1. This process takes 4 moves in total. The constraints ensure that the input positions are distinct and within the valid range, and the problem also accounts for edge cases such as unordered input or large gaps between the stones. By sorting the positions first, we can guarantee correct calculations for both the minimum and maximum moves in all scenarios. To solve the problem of making three stones at positions A, B, and C consecutive, we need to determine both the minimum and maximum number of moves required. The goal is to understand how these stones can be repositioned to create consecutive positions, such as x, x plus 1, x plus 2. To approach this, there are a few key observations. First, for the stones to be consecutive, the gaps between their positions, specifically B A and C B, must each equal 1. This ensures the stones are adjacent on the number line. To simplify calculations, the initial step is to sort the positions A, B, and C in ascending order, so we can always assume A less than B less than C. Once sorted, we can focus on analyzing the gaps between the stones. The left gap, BA, and the right gap, CB, give us the total gap, which is CA. This gap analysis is crucial for determining how many moves are necessary to bring the stones together efficiently. One initial approach to solving this problem is a brute force simulation. The idea is to try all possible sequences of moves, where in each step, one of the outer stones, A or C, is moved closer to the middle stone, B, until the stones become consecutive. While this approach is intuitive, it quickly becomes impractical due to the large range of possible positions, which can go up to 10 to the power of 9. The sheer size of the search space makes the time complexity of this method infeasible. Instead, we can use an optimized approach that avoids unnecessary simulations. By leveraging gap analysis, we can directly calculate the minimum and maximum moves. For the minimum moves, if the gaps are already 1, no moves are needed. If there's a single gap of size 2, only one move is required to fill that gap. Otherwise, at least 2 moves are necessary. For the maximum moves, the outer stones are moved step by step toward the middle until they are consecutive, which requires BA1 plus CB1 moves. This mathematical approach is not only more efficient but also eliminates the need for exhaustive simulations. The algorithm for this problem can be broken down into a series of straightforward steps. First, we sort the positions A, B, and C to ensure they are in ascending order. Then, we calculate the two gaps, gap 1, which is BA, and gap 2, which is seed B. Using these gaps, we can determine the minimum number of moves. If both gaps are equal to 1, meaning the stones are already consecutive, the minimum moves are 0. If one of the gaps equals 2, only one move is needed to make the stones consecutive. Otherwise, at least 2 moves are required. For the maximum number of moves, we calculate the total number of spaces between the stones that are not already filled, which is gap 1, 1 plus gap 2, 1. Finally, the algorithm returns both the minimum and maximum moves as an array, providing the complete solution in constant time. The chosen strategy relies on an optimized approach that simplifies the problem using mathematical properties in gap analysis. This method avoids the inefficiencies of brute force simulation, making it both concise and computationally efficient. By sorting the positions and performing fixed calculations on the gaps, the solution achieves a constant time complexity of O1. Additionally, the space complexity is also O1, as no extra data structures are required. The main trade-off is that this approach demands a solid understanding of the relationships between the gaps and the moves required, which may be less intuitive compared to brute force. However, this trade-off is worth it, as the solution is elegant and directly addresses the problem's constraints. By focusing on gap analysis, we ensure correctness and efficiency, delivering an optimal solution that meets the requirements of the problem. To solve the problem of making 3 stones consecutive on a number line, we start by understanding the setup. The stones are positioned at A, B, and C, and we need to determine how many moves it will take to align them consecutively in the form x, x plus 1, x plus 2. A move allows you to pick up one stone and place it at another position on the number line. The first step of the algorithm is to sort the positions A, B, and C in ascending order so that we can clearly define their relative distances. Let's call the sorted positions X, Y, and Z, where X equals Y equals Z. Sorting simplifies our approach because we can focus on the 2 gaps between the stones, the gap between X and Y, and the gap between Y and Z. These gaps, calculated as gap 1 equals Y x1 and gap 2 equals Z y1, represent the empty spaces between the stones, which will determine the number of moves required. To figure out the minimum number of moves, we analyze the gaps between the stones. If both gaps are 0, meaning gap 1 equals 0 and gap 2 equals 0, the stones are already consecutive, so no moves are needed. In scenarios where one gap is exactly 1, such as 1, 2, 4, only one move is required to bring the stones together. For example, moving the stone at 4 to 3 results in 1, 2, 3. However, if both gaps are greater than 1, like in the case 1, 4, 7, it will take exactly 2 moves to make the stones consecutive. This is because we can close one of the larger gaps in the first move and the remaining gap in the second move. To calculate the maximum number of moves, we sum up the total empty spaces between the stones, which is gap 1 plus gap 2. This represents the total number of moves needed if we only reduce the gap by 1 unit per move. Finally, the algorithm returns both the minimum and maximum moves as min_moves, max_moves. By sorting the positions, we reduce the problem to analyzing the 2 gaps between the stones. The minimum moves depend on whether the gaps are small or large. Smaller gaps require fewer moves, while larger gaps demand more effort to bring the stones together. The maximum moves, on the other hand, are simply the sum of the 2 gaps, as each move reduces the gap by exactly 1 unit. This makes the calculation straightforward. The algorithm accounts for edge cases, such as when the stones are already consecutive or when there's a single large gap. In terms of implementation, the input positions are stored in an array, and an in-place sorting algorithm like quicksort or mergesort can be used to arrange them in ascending order. Gap calculations are performed using simple arithmetic, ensuring efficiency and clarity. Analyzing the time and space complexity of this algorithm reveals its efficiency. Sorting the three input positions has a constant time complexity of 1, because the size of the input is fixed at 3. All subsequent operations, such as computing the gaps and determining the moves, are also constant time operations. As a result, the total time complexity is 1. The space complexity is equally efficient, as the algorithm only requires a constant amount of extra space to store variables like the gaps. Now, let's walk through an example to see the algorithm in action. Suppose the input positions are A equals 1, B equals 2, and C equals 5. After sorting, the positions become 1, 2, 5. The gaps are calculated as gap 1 equals 0 and gap 2 equals 2. For the minimum moves, since gap 1 equals 0 and gap 2 1, only one move is needed, moving the stone at 5 to 3. The maximum moves are the sum of the gaps, which is 0 plus 2 equals 2. Therefore, the output is 1, 2. Let's consider another example where the input positions are A equals 4, B equals 3, and C equals 2. After sorting, the positions become 2, 3, 4. Calculating the gaps gives gap 1 equals 0 and gap 2 equals 0, meaning there are no empty spaces between the stones. For the minimum moves, since both gaps are 0, the stones are already consecutive, so no moves are required. The maximum moves are also 0 because there are no gaps to close. As a result, the algorithm outputs 0, 0. This example demonstrates how the algorithm seamlessly handles edge cases where the stones are already aligned, ensuring that it works efficiently for all possible inputs. This implementation solves the problem of finding the minimum and maximum moves needed to make three stones consecutive on a number line. The solution begins by sorting the input positions A, B, and C to simplify calculations. Once sorted, the gaps between the stones are calculated. Gap 1 is the distance between the first two stones minus 1, and gap 2 is the distance between the last two stones minus 1. To determine the minimum moves, the code checks the gaps. If both gaps are 0, the stones are already consecutive, requiring 0 moves. If either gap is 1 or 0, only one move is needed to make the stones consecutive. Otherwise, 2 moves are required. The maximum moves are simply the sum of the two gaps, as each gap represents the number of moves needed to close it fully. The function returns a list containing the minimum and maximum moves. This approach ensures clarity and handles all edge cases effectively, including when the stones are already consecutive or have large gaps between them. Here, we're starting with the Java implementation of the solution. The first step involves sorting the positions of the three stones, so we place them into an array and use the built-in arrays.sort method to organize them in ascending order. After sorting, the positions are assigned to variables x, y, and z for clarity. Next, we calculate the gaps between the stones. The gap between the first two stones is determined by subtracting their positions and subtracting one more to exclude the stones themselves. Similarly, the gap between the last two stones is calculated in the same manner. These gaps give us the distances that need to be addressed to make the stones consecutive. Moving on, we determine the minimum number of moves required. If both gaps are 0, the stones are already consecutive, so no moves are needed. If at least one of the gaps is less than or equal to 1, only one move is sufficient to align the stones consecutively. Otherwise, when both gaps are larger, at least 2 moves are necessary. Finally, we calculate the maximum number of moves, which is simply the sum of the two gaps, as this represents the total number of spaces that need to be filled between the stones. After calculating both the minimum and maximum moves, we return these values as an array. The first element of the array represents the minimum moves required to make the stones consecutive, while the second element represents the maximum moves. This completes the implementation, providing a clear and efficient way to determine the number of moves needed for any given set of 3 stone positions. To solve the problem, we start with the example where the stones are at positions 1, 5, and 10. First, we sort the positions, which gives us x equals 1, y equals 5, and z equals 10. Next, we calculate the gaps between the stones. The gap between the first two stones, gap 1, is yx1, which equals 5 minus 1 minus 1 is equal to 3. Similarly, the gap between the last two stones, gap 2, is zy1, which equals 10 minus 5 minus 1 is equal to 4. Now, to determine the minimum moves, we check the size of these gaps. Since neither gap 1 nor gap 2 is less than or equal to 1, 2 moves are required. The reasoning here is that we can move one stone to partially close the first gap, and then move another stone to address the second gap. Therefore, the minimum moves are 2. For the maximum moves, we simply sum the gaps. Adding gap 1 and gap 2 gives us 3 plus 4 is equal to 7. So, the maximum moves required are 7. The final output for this example is 2, 7, representing the minimum and maximum moves respectively. Now, let's move to the next example, where the stones are at positions 4, 6, and 8. Once again, we begin by sorting the positions, which gives x equals 4, y equals 6, and z equals 8. Calculating the gaps, we find that the gap between the first two stones, gap 1, is yx1, which equals 6 minus 4 minus 1 is equal to 1. Similarly, the gap between the last two stones, gap 2, is zy1, which equals 8 minus 6 minus 1 is equal to 1. For the minimum moves, since both gap 1 and gap 2 are equal to 1, only one move is necessary to make the stones consecutive. This can be done by moving either the leftmost or the rightmost stone to close one of the gaps. Hence, the minimum moves are 1. For the maximum moves in this example, we add the values of gap 1 and gap 2. The sum is 1 plus 1 is equal to 2, so the maximum moves required are 2. The final output for this example is 1, 2, indicating that a minimum of 1 move and a maximum of 2 moves are needed. Now, consider the third example, where the stones are at positions 7, 8, and 9. Sorting the positions gives x equals 7, y equals 8, and z equals 9. Calculating the gaps, we find that gap 1, the gap between the first two stones, is yx1, which equals 8 minus 7 minus 1 is equal to 0. Similarly, gap 2, the gap between the last two stones, is zy1, which equals 9 minus 8 minus 1 is equal to 0. Since both gaps are 0, no moves are needed to make the stones consecutive. Therefore, the minimum moves are 0. For the maximum moves in this case, we add the gaps gap 1 and gap 2. Since both are 0, the sum is 0 plus 0 is equal to 0. This means the maximum moves required are also 0. The final output for this example is 0, 0, indicating that no moves are needed as the stones are already consecutive. This concludes the walkthrough of these examples, demonstrating how to calculate both the minimum and maximum moves for different configurations of stone positions. The time complexity of the solution involves several constant time operations. First, sorting the three stone positions, A, B, C, using Python's built-in sorted function is efficient because the input size is fixed at 3 elements. Sorting 3 items takes 3 asterisk log 3 time, but since this is a constant value, it simplifies to 1. Next, the gaps between the sorted positions are calculated using simple arithmetic operations like subtraction, which also run in constant time, 1. Determining the minimum moves involves straightforward conditional checks, such as comparing the gap values to specific thresholds. Since the number of conditions is constant, these comparisons also take 1 time. Lastly, calculating the maximum moves is done by summing the two gap values, another 1 operation. Together, these steps ensure the solution's time complexity remains 1 overall. Now, looking at the space complexity, the solution is equally efficient. The input consists of 3 integers, A, B, and C, which require constant space, or 1, to store. In addition, the algorithm declares 3 auxiliary variables, x, y, and z, to hold the sorted positions, and these also require 1 space each. 2 more variables, gap 1 and gap 2, are used to represent the gaps between the positions, and finally, 2 variables store the results for min_moves and max_moves. Each of these variables takes 1 space, as they simply hold single integer values. Even the sorting operation, which is conducted using Python's sorted function, does not require additional memory allocation beyond the fixed input size. Thus, the space complexity of the solution remains O1, as no dynamic data structures or extra memory are used. The absence of iterative simulations or dynamic allocations highlights the efficiency of the solution's design. Unlike a naive approach, which might involve simulating each stone's movement step by step, this optimized solution leverages mathematical calculations to eliminate unnecessary iterations. A naive approach would have a time complexity of O, max, A, B, C, in the worst case, as the number of moves would depend on the initial distances between the stones. However, the space complexity for both the naive and optimized approaches remains O1, as no additional memory is required. By contrast, the optimized solution achieves a constant time complexity of O1, making it far superior in terms of efficiency for all scenarios, regardless of the initial configuration of the stones. In analyzing the best, average, and worst-case scenarios, we see that the solution maintains its constant time and space complexity in all cases. For example, in the best case, where the stones are already consecutive, such as A equals 1, B equals 2, C equals 3, the function still performs sorting, gap calculations, and comparisons. These steps are all O1 operations. In the worst-case scenario, where the stones are far apart, like A equals 1, B equals 10, C equals 20, the same operations occur, and no loops or recursive calls are introduced. This consistency is due to the fixed input size of 3 integers. Mathematically, the big O complexity remains O1 for the time, as each operation is performed in constant time, and O1 for the space, as there are no dynamic memory allocations. This proves the efficiency and robustness of the solution, regardless of the input values. When solving this problem, there are several common mistakes to watch out for. One of the biggest pitfalls is failing to sort the input positions A, B, and C. Sorting ensures that the positions are ordered as A equals B equals C, which simplifies gap calculations and prevents logical errors. Without sorting, the logic for determining the gaps between stones may not work as expected. Another frequent mistake is overlooking corner cases. For example, if the stones are already consecutive, both the minimum and maximum moves are 0. Similarly, when 2 stones are adjacent, the minimum moves required will always be 1, regardless of the third stone's position. Finally, be cautious not to confuse minimum and maximum moves. Minimum moves are determined by edge cases, such as gaps of size 1 or 2, while maximum moves depend on the total distance between the leftmost and rightmost stones. Misunderstanding this distinction can lead to incorrect calculations. Another error to avoid is calculating the gaps incorrectly. Instead of simply using CA, the correct approach is to compute the individual gaps as BA and CB. These adjacent gaps are crucial for determining both minimum and maximum moves, and conflating them into a single value can produce incorrect results. Additionally, hard-coding outputs for specific edge cases, like stones being adjacent, should be avoided. While handling special cases is important, a generalized solution that uses a formulaic approach ensures that your code is robust and works for all possible inputs. Relying on hard-coded values can make your solution brittle and prone to failure if the problem's constraints change slightly. To excel in interviews, it's important to recognize the key pattern in this problem, evaluating the gaps between the sorted positions A, B, and C. Understanding how gaps of 1 or 2 influence minimum moves and using the formula CA2 for maximum moves is essential. Since sorting 3 elements is an O1 operation, the overall logic is constant time, which is a strong point to highlight. Interviewers often focus on your ability to handle edge cases and explain your reasoning clearly, so be prepared to discuss scenarios like stones being already consecutive or nearly consecutive. While the problem involves only 3 stones, interviewers may challenge you to generalize your approach to handle more stones or even a dynamic array. Thinking about scalability and explaining how your solution could adapt to larger inputs will demonstrate your problem-solving skills. Additionally, this problem is closely related to others like LeetCode 1503, which involves calculating distances on a number line, and LeetCode 1040, which extends this problem to more stones and deeper edge case analysis. Other related problems include LeetCode 455, which focuses on sorting and making optimal decisions under constraints, and LeetCode 605, which involves placing elements on a linear structure while adhering to specific rules. These problems share similar themes of optimization and handling constraints. In terms of alternative approaches, one option is a brute force method. This involves simulating every possible move and counting the steps until the stones become consecutive. While this approach can help you better understand the problem, it is computationally expensive and unnecessary for just 3 stones. A more practical approach involves using mathematical formulas to directly calculate the gaps B A and C B to determine the moves. This method is efficient and elegant, but it requires careful handling of edge cases to ensure correctness. For scalability, a dynamic approach can be considered. This involves extending the solution to handle more stones by iteratively analyzing all gaps in the sequence. While this approach is overkill for the current problem with only 3 stones, it becomes useful for related problems like LeetCode 1040, which involves a larger number of stones. Thinking about scalability not only prepares you for more complex variations but also demonstrates your ability to adapt your approach to different problem constraints. By mastering both the mathematical and dynamic approaches, you'll be well equipped to handle variations of this problem in interviews and coding challenges. Great job following along. To summarize, we analyzed the gaps between the stones and used mathematical reasoning to determine the minimum and maximum moves required. This problem showcases the importance of gap analysis and edge case handling. If you enjoyed this video, don't forget to like, subscribe, and stay tuned for more coding walkthroughs. See you next time, and happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!